GPS positioning begins with extremely accurate timing, not with a satellite camera watching your location. Each satellite broadcasts a timestamped radio signal and information describing where that satellite was when the signal left. Your receiver estimates how far away a satellite is by measuring how long the radio signal took to arrive. The receiver's inexpensive clock is nowhere near as accurate as the atomic clocks used by the satellite system. GPS solves position and receiver clock error together from several timed signals. Radio waves travel at approximately the speed of light, so tiny timing errors become meaningful distance errors. The receiver compares transmitted and received timing and converts the delay into an apparent range. A very small timing error can move the calculated position by meters. The first ranges are pseudo-ranges because clock, orbit, and atmospheric errors are still mixed into them. GPS converts time into distance, then corrects those distances before trusting the position. Knowing your distance from one satellite only places you somewhere on a huge sphere around that satellite. More satellite ranges create more intersecting geometric surfaces and narrow the possible receiver position. Several independent measurements let the receiver solve a three-dimensional location. Real receivers usually use more than the minimum number because extra measurements improve reliability and error estimation. GPS is a geometry problem built from overlapping ranges, not a map lookup from orbit. The receiver must solve 3 position coordinates plus its own clock offset. A fourth independent satellite measurement gives the extra equation needed to estimate clock error alongside position. An ordinary receiver can benefit from satellite-grade timing without carrying its own atomic clock. Poor satellite geometry can still produce a weak solution even when 4 signals are technically available. The fourth satellite lets GPS correct the cheap clock inside your phone while finding the phone. GPS signals do not travel through a perfect vacuum all the way to a receiver on the ground. The ionosphere and lower atmosphere change propagation enough to introduce measurable range delays. Receivers use models, multiple frequencies, and correction data to reduce these errors. Atmospheric conditions vary with location, time, and space weather, so no correction is perfect everywhere. Part of GPS accuracy comes from estimating what happened to the signal after it left the satellite. Satellite clocks experience different gravitational conditions and high orbital speeds compared with clocks on Earth's surface. General and special relativity predict clock rate differences that would accumulate into large navigation errors if ignored. The GPS system accounts for relativistic effects so satellite time stays useful on Earth. Relativity is only one item in a larger error budget that also includes orbits, atmosphere, reflections, and receiver noise. GPS is an everyday example of relativity becoming ordinary engineering. Tall buildings can block direct satellite signals and reflect others before they reach a receiver. A reflected signal travels a longer path and can make the satellite appear farther away than it really is. Multipath is one reason a phone position can jump between streets or drift beside tall buildings. Modern receivers combine more frequencies, constellations, and motion sensors to reduce but not eliminate urban errors. When GPS struggles in a city, the problem is often the path the radio signal took. Modern devices often listen to multiple global navigation satellite systems rather than GPS alone. Signals from several constellations can give a receiver more satellites and better geometry. Phones also blend satellite positioning with inertial sensors, Wi-Fi, cellular information, and map constraints. The exact data sources and accuracy depend on device hardware, permissions, surroundings, and software. The blue dot is usually several positioning systems working together, with satellite timing at the core.